In this video, I will go over the quiz questions on Chapter 10, Gases. First, Q1024 Preview. One ATM is 101.325 pascals. That's from the textbook or from the internet. One ATM is equal to, well, first, it's 1.01 bars. 1 bar is 10 to the power of 5 pascals exactly. 1 ATM is roughly 760 millimeter mercury or 760 torrs. 1 torr is 1 mmHg. So these two numbers are approximate numbers because really it depends on the gravitational acceleration and even temperature. Over here, pound per square inch. Again, this is just by definition. 1 ATM is 101.325 pascals. And over here, you can convert pound to Newton and per square inch to per square meters. And then you'll see 1 ATM is roughly 14.7 psi. 1 bar is roughly 14.5 psi because 1 bar is slightly smaller than 1 ATM. The typical tire pressure is equal to, okay, we have 4 different units here. So over here, we have 30 to 35 psi. So let's take the average, roughly 32, 33 psi, divided by 14.7. I think it's roughly 2.3 ATM, and therefore it's roughly 2.3 bars. Again, 1 ATM is roughly 1.01 bar, or you can say roughly 1 bar. This number is off by a factor of 10. Charles' law tells us the volume of gas is proportional to, okay, the volume of gas is proportional to the number of moles N, inversely proportional to pressure P, and then proportional to temperature T, so NPT. And then I would just remember ABC correspond to NPT in alphabetical order. ABC are the Avogadro's law, Boyle's law, and Charles' law. So ABC, NPT, therefore just pick temperature. Again, ABC, NPT, so it's going to be 1 over P. It's not P. The higher the pressure, the smaller the volume. You can squeeze a balloon just to verify this. The volume of 1 mole O2 is how many liters? Actually, the volume of 1 mole of almost any gas is roughly 25 liters at this room temperature and 1 bar pressure. What you need to do is you do just PV equals RT and then plug in numbers. You just plug in volume is 0.0 you just plug in pressure. Pressure is 10 to the power of 5 pascals. Temperature 298 Kelvin. R is 8.31446 joule per mole per Kelvin. And then you get the volume. Volume is roughly 0.025 cubic meter. And remember, 1 cubic meter is 1,000 liters. So the answer is 25 liters or 0.025 cubic meter. The density of CO2 is roughly what? At 298 K and 1 bar. Again, the molar volume of any gas is roughly 25 liters at the room temperature and 1 bar. So you just need to know the mass of 1 mole CO2, which is 44 grams. 12 for carbon, 16 for oxygen twice. The total is 44 grams per mole. The molar volume is 25 liters per mole. So you just need to use 44 grams divided by 25 liters. The answer is 1.8 gram per liter. So over here. Then let's submit the quiz. Alright, 7 out of 7. So we're done with this. 10.324. So I'm gonna open this. 7 more questions here. Preview. The gas constant R is equal to how many joule per mole K? This is the SI unit, so 8.31446. This number is correct only if the unit is ATM liter per mole K. This is because ATM is 1.01 bar and 1 liter is 0.001 cubic meter. So you need to adjust this gas constant accordingly. Gas pressure results from the collisions, that's for sure. So let's look for the keyword collisions between the moving gas particles and the surface of the container. All right. N2 has a greater molar mass than H2. Compare the pressure of this N2 and this H2. Well, what you really need to do is you ignore this first sentence, because you just need to use PV equals nRT to compute the pressure of N2 and H2. Over here, PV equals nRT, so the pressure is nRT over volume. So you have N times R times T divided by this volume. And over here again you have N, you have T, you have volume. So because R is the same for these two gases, so what I will do is I will just do NT over V. So N2 times T, I'm gonna say roughly 300. Oh, and by the way, the temperature is the same, so I just need to compare N over V. So N over V is 0.04. Over here, 4 over 100, 0.04. So they're about the same. But if you really want to compute the pressure, it's possible. You just need to use nRT over V. But make sure that you use units consistently. I'd prefer to use SI units whenever I can. But you can also use ATM at liter. You just need to make sure R is 0.08206 ATM liter per mole K. But if you use SI unit, R is 8.31446 joule per mole K. So pay attention to the units. O2 has a greater molar mass than H2. Okay, over here, this molar mass does matter. The speed is proportional to the square root of 1 over the molar mass. Therefore, H2 moves faster than O2 at the same temperature. So, all right. Again, the speed is inversely proportional to the square root of the molar mass. Hydrogen is lighter, therefore it moves faster. I'm assuming the temperature is the same. The molar mass of N2 is 0.028 kilogram per mole. This is a very simple question. The purpose of this question is to remind you to pay attention to the units. And kilogram is the SI unit of mass. Very often students use grams as the SI unit of mass. That's wrong. At the room temperature, the root mean squared speed of N2 is roughly how many meters per second. So here is an example, but really you just need to do the square root of 3RT over the molar mass. That's it. So 3 times R times temperature over the molar mass. So 3 times 8.3, that's R, times room temperature 298 and divided by 0.028 over here. So the molar mass of N2 is 0.028 kilogram per mole. And when you do that, you'll get the speed, roughly 500. Helium and neon are noble gases at the same temperature. The ratio between, again, helium moves faster than neon because helium has a smaller mass. The molar mass of helium is 4 grams per mole. The molar mass of neon is 20 grams per mole, so the ratio is 1:4 ratio. This time I didn't convert gram to kilogram because I'm just computing the ratio. It's 1:5. Therefore, the speed ratio is the square root of 5:1. So remember I said square root, and I reversed the ratio because the ratio of the speed is inversely proportional to the square root of the ratio of mass. Again, it's inversely proportional, and there's a square root. Square root of 5:1 is square root of 5. Square root of 5 is 2.2-ish. So, submit quiz. There are 7 questions. We got 7 out of 7. And let's move on. Okay. Over here, there are a total of 14 questions. I'm going to click preview so that we can see this 14 questions. Number 1, a gas particle collide 1,000 other particles during its travel of 50 micrometers. So over here, after this many collisions, actually there are 999 segments, but approximately 999 is 1,000. All right, so what we should do is just 50 divided by 1,000. Well, don't forget about unit. Micrometers. So 50 micrometers divided by 1,000 is 50 nanometers. Again, this is because 1 micrometer is 1,000 nanometers. Pay attention to the units. Micro means 10 to the power of -6. Nano means 10 to the power of -9. When a bottle of perfume is spilled, the perfume molecules it's diffuse. When we're talking about effusion, you need a tiny hole that allows only one particle to pass through at a time. Diffusion depends on the difference of the concentration in space. A nitrogen gas is confined in a box. We then poke a small hole, over here, with a diameter of only 5 angstroms to allow just one nitrogen molecule to come out at a time. It's effusion, that's by definition. The effusion rate is doubled when its temperature increases 4-fold. This effusion rate is proportional to the speed of the gas particle, and the speed of the particle is proportional to the square root of the temperature. So the square root of 4 is 2. So if we increase the temperature 4-fold, the speed increases 2-fold. If we increase the temperature 100-fold, the speed increases 10-fold. The molar mass of helium is, the molar volume, we'll just use PV equals RT again. So V over N, that's the molar volume, and V over N is RT over P. So we're just plugging RT over P. I'm going to use R 8.3 times this temperature, and then divided by this is actually 50,000 pascals. So basically you have 8.3 times 600 RT, that's 5,000, divided by 50,000. So I think the result is 0.02 cubic meter, and that's roughly 25 liters. Sorry, I just estimated the number. 25 liters per mole, the molar volume. So I didn't pay attention here. The molar volume, so that means volume per mole. 25 liters per mole. There's another trick to do this quickly. So if you remember, the molar volume of any gas is roughly 25 liters at the room temperature in 1 bar. And then now we double the temperature. So the molar volume should be doubled, but the answer is this. I'm sorry. I got messed up. So first, the molar volume of pretty much all gases is 25 liters per mole, at the room temperature in 1 bar. And now we doubled the temperature. That will double the molar volume. and we reduce the pressure to 50% of its initial value or room pressure. Therefore, the molar volume of the gas should be quadrupled. So we should use 25 times 4, 100 liter per mole. Another way to do this, again, we can just use PV equals RT. So V over N is RT over P. RT, R times T, R is 8.3 joule per mole K, temperature is 600, pressure is 50,000 pascals. So really it's just 8.3 times 600 divided by 50,000. The result is 0.1 cubic meter. Okay, again, I used SI units for every single number. So the result must be also in the SI unit. The result is 0.1 cubic meter, and therefore per mole. Therefore, it's 100 liters per mole. Again, 1 cubic meter is 1,000 liters. The molar volume of a gas doubles when what doubles? Temperature. What about this one? Okay, if I change the question by deleting this molar, okay, and then this is also a correct answer. But I'm asking about the molar volume, so it's volume divided by N. V divided by N. If you double the number of moles, you double the volume, so therefore there's no change, all right? Question 7. The mole fraction of O2 is 0.2, then the partial pressure is 0.2 times the total pressure, which is 1 atm, therefore the result is 0.2. I remember that 1 atm is defined to be the pressure of air at the sea level. So it's 1 atm at sea level for air, 0.2 for O2, 0.79 for nitrogen. There's 1% of other gases, mostly CO2, water vapor, and argon. The mole fraction of helium, neon, argon is this. So together it's 100%. The partial pressure of neon is 0.4 bars. Remember, the partial pressure of neon is the mole fraction of neon times the total pressure. So the total pressure is the partial pressure of neon divided by the mole fraction of neon. You get 2 bars, so the first blank 2 bars. And then 2 bars times 0.1, the mole fraction of helium, you get 0.2, so 2 and 0.2. For a real gas, the larger the size of the gas, well, the higher the pressure. The reason is very simple. If you have really large gas molecules, they occupy more space. So effectively, that reduces the available volume. And then remember, PV equals nRT. Pressure is inversely proportional to volume, but over here, P is inversely proportional to the available volume. The volume of the container subtract the spaces occupied by those gas molecules. So the larger the size of the gas molecules, the smaller the available volume, and therefore the greater the gas pressure. The attraction between water is greater than CH4 at the same temperature, which gas has the lower pressure. Oh, I'm sorry about this. I meant to say molar volume here. But anyway, water. Just imagine the extreme case. If the attraction between water molecules is really, really high, all those water molecules is going to stay together with each other. That will effectively reduce the number of collisions between the water molecules and the surface of the container. So, water. Yeah, again, just, if you are just comparing two different types of molecules, or in this case, 2 molecules, think of some extreme cases. Just say, well, what if the attraction between water molecules is so huge that, all those water molecules are attracted to each other, they stay with each other, and then how many collisions will there be between the water molecules and the surface of the container? Nearly 0. No collisions, no pressure. A real gas may behave like an ideal gas when the molar volume of the gas approaches infinity. So when the molar volume of the gas approaches infinity, that means first, the volume of the container is so much greater than the size of the molecules that we don't even need to take the size of the molecules into account. And two, when the molar volume approaches infinity, there's another benefit. The distance between the molecules is huge. That means the attraction between gas molecules is negligible. And then this real gas behave like an ideal gas. All right, and also we can just think of another extreme case here. Let's say, what if the molar volume approaches zero? Well, obviously this gas will behave more like a solid or a liquid when you are compressing this gas to a very, very small molar volume. Question 12, the molar volume of a gas increases when molar mass is irrelevant. Pressure, okay. The volume increases when pressure decreases. Okay, well, it's just Boyle's law. So when temperature decreases, actually the molar volume decreases. And mean free path is not quite relevant either. So again, PV equals 1 RT, so volume is inversely proportional to pressure. Estimate the value of parameter B. B is the size of the molecule. So what we need to do is very simple. If we just need to know the size of a molecule, why don't we just compress 1 mole such molecules together and measure its volume and then divide it by the Avogadro constant. So that's what we do. We compress this water vapor into maybe solid. It's easier to compute. It's going to be 20 milliliters. For liquid, well, it's also easy, 18 milliliters. The reason is 1 mole water weighs 18 grams. The density of liquid is 1 gram per milliliter. Solid 0.9 gram per milliliter. So it's either 18 milliliters or 20 milliliters. And then that's the volume or the size of 1 mole molecule. So be sure that you use the right unit. It's 20 milliliters per mole over here. Okay. So again, the physical meaning of this B is the size of 1 single molecule multiplied by the Avogadro constant. So that's this. Question 14, attraction. We're talking about attraction. Over here, read this. Molecules with a non-zero dipole has greater attraction. So let's look for a molecule with non-zero dipole, NH3. H2 has a zero dipole. CH4 has a zero dipole. Although the electron negativity of carbon and hydrogen are slightly different, but you have 4 bonds there. The bond polarities of these 4 bonds cancel each other. Well, helium, the attraction between helium atoms is the smallest. Alright, let's take a look. 14 out of 14, so we're good.